Hi there, how's it going? In this Mechanics of Solids video, I'm going to go through a simple deflection problem. So let's have a look at the problem. Rightio, so here it is. We have this steel rod with some loads acting on it. So we've got an end load here of 40 kilonewtons and then a couple of 50 kilonewton loads acting partway along the rod. And we're asked to determine the displacement of NC. So NC out here with respect to the fixed support at A. Right, so we need to think about our solution, and if we're going to use this equation, so most of or many of you would have seen this before. Some of you may know it as split flea, force times length over Young's modulus and area. But if we have a component like this with multiple loads along its length, then we can use this form of the equation that says that the sum of the deflections in each part of the component between the loads, add those all up, and we get the total deflection of the rod. Okay, so to use this equation, split flea, or FL over EA, or in our case here, NL over EA, this is only valid if the strain is uniform within each section. In this case, we can assume that will be the case, except for around the end here where the load is applied, in the middle here where the load is applied, and at the end. But due to St. Venant's principle, we can make the assumption that the strain is uniform throughout the length and do this calculation. When we think about this equation, in the past you may have thought of, if you know the equation from engineering studies at school or somewhere like that, and you know it as FL over EA, so you may have been used to thinking about that F, the force that was here, as an external load, right? You should try and get out of that way of thinking and think about this force here that's in this equation as an internal action. And in this case, we're looking for the internal normal force. Now, in some instances, that internal normal force will be the same as the external force, but not always, as you'll see for section AB. All right, so what we need to do is to follow our stress analysis process, take a cut through the section, determine our internal actions. So in this case, we're just going to have normal forces as internal actions. We'll apply our equation of equilibrium, sum of the forces in the horizontal direction equals 0, to find our internal action. Now you can probably do this in your head, but I recommend that you don't. I recommend that you follow the process and justify what you do so that someone else can come along and check your work. For a simple problem like this, sure, you could do it in your head and just write down the answer, but someone coming along and checking your work can't see inside your head. They have to rely on what you've written down. Okay, so we're going to take a cut through the section between B and C, draw our free body diagram. So we've got an external load of 40 kilonewtons, and then internally we've got our internal action, and usually we'll draw the internal normal force in tension. So always draw the force acting out of the surface to indicate tension, and then if you get a negative number, then that will indicate that the section that you're looking at is in compression. All right, so using our sum of the forces in the horizontal direction equals 0, we can easily see that the internal normal force NBC here is equal to 40 kilonewtons. If we now look at the section between A and B, do the same thing again, take a cut through section AB, look at the whole of the left-hand side or the whole of the right-hand side. So we're going to look at the whole of the right-hand side. So that means we need to include section BC in this free body diagram, right? And a lot of students ask me, why do we need to put this out here? Why can't we, why don't we just look at this little bit here between the cut and B when we're looking at section AB? It's because all of these forces out here are generating the internal force at this section that we're looking at. All right, so if we put on our internal normal force, NAB, again, assume that it's in tension. So put the arrowhead or the arrow directed out of the surface, indicating tension. From sum of the forces in the horizontal direction equals 0. So using our equilibrium equation that we've got here, we can easily see that NAB plus 100 minus 40 equals 0. So if we rearrange that, we get NAB must be equal to minus 60 kilonewtons for this to be in equilibrium. Because we've got negative sign here, that tells us that this section is in compression. The area of a circle, pi d squared on 4, or if you like, pi r squared. R is equal to d over 2, so d over 2 all squared becomes d squared on 4. And we need to know the Young's modulus, and we're told that it's A36 steel, so you can either look up the table in the textbook, or you can use an online materials database like MatWeb, and I show you how to use MatWeb in some of my other videos. But if you do that, you can look up and see that the Young's modulus for this steel is 200 gigapascals. And you should know that all steels are going to have a Young's modulus of around about 200. Some might be 190 odd, some might be 210, but yeah, they're all pretty much have the same stiffness and therefore the same Young's modulus of around about 200 gigapascals. Okay, so now we know our internal forces that we can put into this equation. Our lengths are given up here. We know our cross-sectional area, and we know our material properties. So we can start to now use this equation. I'm going to work in newtons, millimeters, and megapascals. If you're not comfortable with doing that, you can work in newtons, meters, and pascals. But I just know that in most engineering problems, my stress values are going to be in megapascals and deflections are going to be in millimeters. So I like to work in this set of units rather than newtons, meters, and pascals, and then having to convert at the end. Right, so putting in our values. So let's have a think about what's going to happen with this component. So we can see that the component BC is in tension. Right, so if we didn't have section AB here, if it was just built in or held stationary at point B, section BC is going to get longer and point C is going to move to the right. Okay, so that's what we've got here. 40 kilonewtons, so 40 by 10 to the 3 times the length of section BC, which is 400, divided by the cross-sectional area and divided by the Young's modulus or modulus of elasticity in megapascals. Right, so here it's given in gigapascals. So giga is 10 to the 9, mega is 10 to the 6. So to convert this into megapascals, we just have 200 by 10 to the 3. Okay, so that's what we get for this first bit, but that's not all that's going on, right? So the other thing that we know is that from our drawing our free body diagram here of our section AB, we know that section AB is in compression. So this is going to, AB is going to get shorter. So this whole section BC is going to move to the left because this part's in compression. So we'll call that negative. So we'll add our compression here into this equation. So we've got the sum of the deflections for each of the bits. Positive here is to the right. Negative is in compression. So this part will go to the left. All right, so our normal force here that we calculated was 60. Okay, so again, I say try and get into the habit of thinking about this formula as this force here being the internal action, not an external force. Okay, if you're thinking about it as an external force, you might be tempted to put in here 100 or something, right? But we, as I said, we use the internal force. So the length is given 600 millimeters, same area, same material. Do our sums and we get minus 0.3183 millimeters. Okay, so that tells us that this point B here moves more to the left than the stretch of BC on its own. Right. So we can round that up to 0.32 millimeters and just say that it's point C here will be moving to the left, right? Because of the compression, the greater compression in AB than the stretch in BC. All right, so that's it for the problem. Hope that was helpful and maybe a little bit interesting. That's it for now. See you in the next video. Bye.